Hello and welcome to this lecture. In the last lecture, we saw a series and what does it mean for a series to converge, root test, ratio test, and how to find convergence and establish convergence, etc. Now we are going to move towards power series. So let me remind you of what the power series is. How did we define it? So you start with a sequence of real numbers ak, a0, a1, a2, etc. And then you fix a real number x in R. So this x is like a variable. I'm going to think of it as a variable, arbitrary real number, but you can think of x as fixed for the purposes of this definition to make it understand clearly, make things more clear. And then you look at the sequence ak x power k. Okay, and this is just a small, slightly different sequence here. For every a2, we do a2x squared like that, right? So this x plays a role now in this sequence. And then you look at partial sums of this sequence, this ak x power k, and that I'm going to call Sn of x, and that will go all the way up to, let's say, k equals 0 to n. This notation sigma, you remember, right? So sigma k equals 0 to n means this quantity is evaluated for each value of this k in this range 0 to n, usually integer, right? 0, 1, 2, 3, etc. And then you add it all up. So you get a0, a0 plus a1x, a0 plus a1x plus a2x squared, so on. Okay, and then the power series is basically the limit of this partial sums as n tends to infinity. So if you want to be very precise, you can write summation k equals 0 to infinity akx bar k, which is a0 plus a1x plus a2x squared plus dot dot dot, goes on forever. Now this k equals 0 and infinity is usually swallowed in the notation. Nobody really bothers about where you start because it goes all the way to infinity. What matters is only after a certain point. So this k equals 0, of course it matters exactly when you want to know the function exactly, but only when it matters people put it. Usually they just write summation akx bar k. So here's an example, a very famous example which we really wanted because this seemed to have some property that we wanted, right? So this kind of function, if you could differentiate term by term, it was its own derivative, and this was something that was very interesting for us. But to really do it, we have to ask these kind of questions. So for what x does the power series converge properly? How can we think of this as a function of x? What is the derivative of this function with respect to x? Is it continuous? Is it differentiable? These kind of questions crop up, and we're going to resolve all this in this lecture and the next one. Okay, so let's get started. So let's try to visualize. This visualization is a little bit important. Quite often when you write these expressions, it's good to also have a mental picture of what's going on, and this is the visualization. So here is this this power series. I'm going to call this exp of x. Okay, it says capital exp here, so this means I might use just small e also. So exp of x. This is a notation. We'll see why this is exp later on. Okay, so it has several wonderful, interesting properties. So this is the power series I'm interested in. How do I visualize it? So this is a very important and easy way to visualize a power series. You take the partial sum function Sn of x, which is a polynomial, right? 1 plus x squared by 2 factorial, so on till x power n by n factorial. For different values of n, I can plot this polynomial as a function of x. This is what I've done here. X goes from 0 to 5, and I'm plotting Sn of x for different values of n. What are the values of n I've considered? I've considered n equals 4, which gives you this blue line here, this curve, and then n equals 8, which gives you this green line here. Okay, and then I considered n equals 16, which gives me the black line. Okay, and then I considered n equals 32, which gives me the black crosses. Okay, just the crosses. Okay, so you see here, as you increase n, this Sn of x seems to converge to some shape, right? See, 4 was really low, 8 was a bit higher, 16 was even higher, but then 32 seems to be right on top of 16, at least up to 5. Okay, and this seems to happen from 0 to 5. Okay, the x range is from 0 to 5, and here and all the convergence seems to be very rapid. Even by 4, the convergence has happened between 0 and 1 and all that. But as you go higher and higher, it looks like you may have to go to larger and larger n. But nevertheless, the final shape of this curve for large enough n, right, seems to work out quite okay. So this is the way in which one can visualize the convergence of these power series expression. As n increases, Sn of x seems to tend to some shape. Okay, so it's different from the convergence of numbers, right? If you remember the convergence of numbers, we use these stem plots, and whenever that stem plot seemed to be hovering around one particular line, it getting closer and closer to that line as n tends to infinity, that's convergence of a sequence of numbers. Okay, so that was easy enough to understand. So here, for every x, you have to worry about that. So how do you think of this? Here's another way to think of it. You fix a particular x, let's say x naught, and draw this vertical line. Okay, you get a series now, right? When x naught is fixed, you get a 1 plus x naught squared by 2 factorial, so on. This is a series, and if you evaluate it at the 4th term, you'll get this value. 8th term, you'll get this value. 16th term, you'll get this value. 32 is also somewhere there, etc. So for each x naught, you get a particular series, and that converges by ratio test, right? So this series will converge by ratio test. What do we mean by that? What is ratio test here? So the series 1 plus x naught squared by 2 factorial plus so on has an equals x naught power n by n factorial, right? Now, what does the ratio test tell you? An plus 1 by an, we have done this before, x naught power n plus 1 by n plus 1 factorial divided by x naught power n by n factorial, and this, if you cancel the common terms, you will simply get x naught by n plus 1. This tends to 0 as n tends to infinity. Okay, so the ratio test clearly tells you that this converges for all, this sequence converges, right? So this sequence converges. The ratio test makes it really very clear, and value of x naught does not matter. Whatever x naught I pick, for all x naught, any x naught I pick, since n is tending to infinity, x naught is only some finite value. Eventually, this value will go off to 0. So for any x naught, this series converges. Okay, that's the convergence by ratio test. Is very easily established. Okay, so suppose it converges to fx naught, right? So this fx naught will change with x naught, no? As you keep changing x naught, this where this converges to will change, and that is that limiting function, right? So here it seems to converge somewhere to here. If x naught is this guy, it seems to be converging somewhere around 85 or something like that, right? So that's the value where it's converging to. Likewise, another x naught close by, it will converge to another value, and this gives rise to that one smooth curve. I mean, I don't know, we haven't established smoothness yet, but one curve for this fx naught. Okay, so if you plot fx naught for different x naught, you get a curve. This is what I've done here. Okay, so this is exactly what has happened here, and this defines a function of x. Okay, so that's how you have to think of this 1 plus x squared by 2 factorial, x cubed by 3 factorial, etc. As you keep changing n, as you keep increasing n, this series of functions hopefully are converging to something, and we are thinking of that function. Okay, I hope it's clear to you. That every x naught you get a series, and all the x naughts together you get the power series, right? So that's how it works. So let's do a few more of these visualizations. It's nice. The next very important series is geometric series. We've seen that before, and you can also have a geometric power series, right? What is geometric power series? 1 plus x squared plus x cubed plus so on. Previously we had r, and we thought of r as a constant. What happens in the geometric power series is we're going to think of the common ratio as x, and the x is a variable, right? So x is a real number, and for different real numbers x, we're going to study what happens to this series. Okay, so if you just plot it, I'm just plotting it here. Later on we'll see that this is actually equal to 1 by 1 minus x, right? We know that this is 1 by 1 minus x. For x bit for mod x less than 1, this will converge to 1 by 1 minus x. We know that from the geometric series. So that's sort of brought out here very clearly. So here I'm plotting x less than 1. You see close to 1, 0.9, 0.91, 0.95, etc. For n equals 4, I get something way below. N equals 16, I get something there. N equals 64, I get the black line. For 256, I get the black crosses, and for 512, I get this magenta line, which is right on top of it. So this is also converging, and it converges to 1 by 1 minus x for mod x less than 1. We know that. Okay. So what happens when x is greater than or equal to 1? If I plot here for x greater than or equal to 1, I know this is going to diverge, right? And you can see the divergence here. For every value of x greater than 1, it's not really converging. As I increase n, I go higher and higher and higher. So as you go a little bit away from 1, it's much more easier to see. Look at this 1.02. At 16 and 4, it seems to be here, then 64, and then by 256, it has gone off to some 8,000. Okay, so we know this is also true for the geometric series, right? So 1 by 1 minus x, it does not converge to 1 by 1 minus x for x greater than 1, right? For x equal to 1, it just goes 1 plus 1 plus 1 plus 1, it diverges, and for x greater than 1, it diverges even faster, as you can see in this picture. So this kind of behavior is very typical for a power series. If you take any power series like this, there will be this one critical sort of value, this 1, right? In this case, it's 1. And for x less than 1, less than that critical value, convergence will happen. And for x larger than that critical value, the series will diverge. Okay, so this is sort of a very interesting property for power series, and it turns out to be very generally true. In some very general sense, it is true. We'll see later on how that works. So here's one more example before we close. Once again, the series is x plus power series is x plus x squared by 2 plus x cubed by 3, so on. And if you make a plot, so in this case we don't know where it converges, right? We don't know, like 1 by 1 minus x and all geometric series, we don't know exactly where this converges. But nevertheless, if you plot it, you notice once again something very similar happens. For x less than 1, it seems to converge to some shape. Okay, we don't know what that shape is, but some shape. And for x greater than 1, it you can see clearly it diverges. It just jumps and it's jumping off to infinity here. Okay, so like I mentioned, this behavior is very typical of power series, and we will see why that is so in the next theorem. So here is the theorem. It's called it defines something called the radius of convergence of a power series. How do you think of that? Here's the example. Is the statement of the theorem. Let's read through and understand it. We're looking at a power series summation a n x power n, and I'm going to assume this particular limit exists and it's equal to alpha. What is this limit? We have seen this before. It comes in the root test, right? Mod a n raised to the power 1 by n. This limit as n tends to infinity has to exist and let it be equal to alpha. Okay, so that's how I'm going to say it. So this is the root test limit, and the root test limit is alpha. I'm going to define r to be 1 by alpha, the reciprocal of alpha, and I'll keep this notation going. If alpha is 0, I'm going to say r is infinity, and if alpha is infinity, I'm going to say r is 0. Okay, so the 1 by alpha sort of captures this typically, but I want to make it explicit, so I'm putting that down there. Okay. So if this were true, if there is an alpha for which this limit exists, this root test limit mod a n power 1 by n exists, then this power series converges if mod x is less than this r, and it diverges if this mod x is greater than r. Okay. So we saw this typical behavior in a couple of examples, and guess what? It's true in general whenever this root test limit exists for the sequence a n. Okay, very nice, isn't it? So this alpha limit works out. And this r, this value r is called the radius of convergence. Why is it the radius of convergence? You can see when up to r it converges, beyond r it doesn't converge. Why radius? Because there is a circle sort of thing that happens when you move from real numbers to complex numbers. We haven't gone there yet, but for real numbers, also for consistency, people say radius of convergence. You can also call it length of convergence if you like, but this is radius of convergence, and that's a typical notation. A proof is actually very simple application of root test. Before I show you how that works, I'll just show you the proof. It's very easy. But one thing I want to tell you, this alpha we can also find by ratio test, right? You need not, we saw that limit connection between ratio test and root test, right? This limit, and if the ratio test limit also exists, right? Limit as n tends to infinity, absolute value a n plus 1 divided by a n. If that limit also exists, alpha is also equal to that. We know that is true. So we can use the ratio test also to find alpha. So even if you can't evaluate this limit, you can evaluate it using the ratio test. But why is this following from the root test? It's very simple. So you can just fix x. So if you look at the series, you fix x, and you look at the series 1 plus I'm sorry, not 1, a0 plus a1x plus a2x squared plus so on. The nth term is a n x power n, and the root test limit L equals limit as n tending to infinity, absolute value of a n x power n. Okay. Now, what is this absolute value? This is raised to the power 1 by n. This is absolute value of a n raised to the power 1 by n times absolute value of x, n times 1 by n, and that's just 1, right? So it just becomes absolute value of x. Okay. Now, this is alpha times mod x. Why? Because this limit tends to alpha, right? This is a n 1 by n, this is by assumption. So alpha times x. So if L is less than 1, which is the same as mod x less than 1 by alpha, converges, right? Series converges. And if L is greater than 1, just by the root test, which is mod x greater than 1 by alpha, and this is defined as R, isn't it? Series diverges. Okay, so that's that's the one. If it's equal to 1, of course, that's inconclusive. So, but anyway, it will work out squared. Okay, usually it will diverge at that point also. Okay, all right. So this is a very simple proof of this fact, and radius of convergence is firmly established. So one skill that you need to develop, given a series, you have to find the radius of convergence, right? So here's a bunch of series I've shown here. How do you find the radius of convergence? First thing is to apply the ratio test and see if you can find alpha. Okay, no need to do the root test. Root test you can do if ratio test doesn't work, or you can try the root test. If it seems confusing, you go to the ratio test, right? So ratio test is always a very, very useful thing to do. Let's just quickly do all these examples. The first example is geometric, and you have 1 plus x squared plus so on, and the nth term is, let me write the nth term here, x power n, so on. It's just 1, right? An equals 1 for all n. So you can even do the ratio test here. Alpha is limit as n tending to infinity, absolute value of an divided by 1 raised to the power 1 by n, which is 1 raised to the power 1 by n, which is 1. So alpha is 1, and you can see the radius of convergence is 1. Not surprising, we know that this is equal to 1 by 1 minus x if so in fact we know that this converges to 1 by 1 minus x if mod x less than 1, right? So all of this we know, but anyway this test also tells you what it is. And then you have the sequence nx power n minus 1, which is 1 plus n equals 1 to infinity, right? So be careful here. So 1 plus 2x plus 3x squared plus so on. Okay. So if you have to write down the an is n minus 1, right? Oh, sorry, n plus 1. An is n plus 1, isn't it? So n equals 0, you get 1, n equals 1, you get 2, n equals 2, you get 3, so it's n plus 1. So if you try alpha here with the root test, it will be a little bit more confusing. So root test is not a good idea. You can use the ratio test here. Limit as n tends to infinity, absolute value an plus 1 by an. This will work out to something very, very nice. Limit as n tending to infinity, n plus 2 by n plus 1, and this will be 1, right? So this limit is 1. You can easily evaluate it. If you try the root test, what happens to the root test? You will be stuck with some limit like 1 plus n raised to the power 1 by n. You may know this, I mean, it's something slightly advanced. We will maybe see it a little bit later. But these kind of limits are a little bit more confusing, but the ratio test gives you very, very simple answers, right? So this is the second one. I'm going to leave the third and fourth as examples. I mean, fifth also we saw just now, but fifth and sixth alone I'll do. Third and fourth are very similar. You'll get radius of convergence to be 1, right? So that's what you'll get for both of those. Okay, I'll leave you as an exercise. Ratio test will work plenty well. It will work. It's very easy to see how ratio test will work here. So 5 and 6 alone I'll do very quickly. Okay, 5 is an is 1 by n factorial, isn't it? So again, ratio test is the easiest to find this alpha. Absolute value of 1 by n plus 1 factorial divided by 1 by n factorial. So that will be just going off to 0. So this gives you a very interesting, so by the way, here r is 1. So in this case, if an is 1 by n factorial, you got r equals infinity. Okay, so that's very nice. So this, for the first time, we're getting this expression that then this exp of x that we had, which is 1 plus x squared by 2 factorial plus x cubed by 3 factorial, so on, it converges for all x. For all x in real, plus minus everything, right? Mod x less than infinity, that's all of the real numbers. This exp of x converges. It's very nice, isn't it? So this function, this 3 factorial, 2 factorial is so big, the n factorial is so big that any x power n, it's able to kill it and make it a convergent series, right? So that's very, very important to know. Okay, so this is the fifth one I wanted to do. The last one is just to show you that if you have the series n power n x power n, so in this case an is n power n. So here the root test will work. Alpha is limit as n tending to infinity, n power n raised to the power 1 by n, which is infinite, right? So this is a case where this results in radius of convergence of 0. So this converges nowhere, right? Converges nowhere. Okay, so this is all nice terminology. Diverges everywhere, converges nowhere. So that can also happen. So that's why I wanted to do 5 and 6 typical examples of what can happen. So this is a skill, a very important and simple skill to pick up. Given a series, what is the radius of convergence?